Hi everyone, welcome. This is the video on the science of the voice. So what I'm going to do is actually talk a lot, put some physics into how we speak. Now I'm going to tell you right up that I am not a biology person, so if you want really detailed mechanics on voice and speech, a speech pathologist might be the person to talk to you about. What I want to do is just take some of those everyday things that we notice about voice and speech and kind of put some physics to it, teach you a little bit about how physics kind of governs the voice. So I'll start off with some basic things such as breathing. There's a gas law that actually explains why we breathe and how we do that. I'll talk about a little bit of the anatomy of the voice. We'll talk about speech too. Why whispers sound the way they do versus vowels and consonants, and this thing called formants. I'll talk a little bit about articulation and projection, and then we're going to talk about things as a closed pipe system. So our voices kind of act that way, and there's consequences for that. And if you're doing the class, we'll also have a lab doing this. So I'll explain what we're going to be doing in lab as well. So to make speech or to voice or to sing, you actually need two things. These things seem obvious, but it's worth, talking about. But you need something, of course, to make the sound. And, of course, we use air specifically. So our lungs and air and our voice box are the things that make the sound. And then we have modifiers that change the sound or that filters the sound. So that's the lips, the tongue, the vocal folds. You could actually change air, and I'll talk a little bit about that too as well. So you need two things to actually speak, right? For obvious reasons, if you had no air, then you can't talk. If you're in space and you're in that, unnatural habitat of no air, you wouldn't be able to draw in air at all because there's no air to draw in. So yes, you can make these predictions. And also that if you can't function your tongue and your lips properly, you can't form words and specific things. So that's, again, when the speech pathologist, kind of comes in and does that. Now, I remember when I was younger, I had a little bit of speech. I still have a little bit of, pronunciation issues and whatnot. But you might have, maybe you have children if you're older that might go to speech. But I notice it now as an adult with my daughter. It's so interesting watching her grow up. But she doesn't have the correct tongue and lip placement to say some things. So because of that, her speech is a little off. That's why children kind of speak funny. So they actually speech pathologists actually work with kids to speak with correct diction and articulation and proper tongue placement. So it's a whole career really is to help correct speech. So anyway, let's start off with some physics because this is a physics class, and I'm actually going to talk about a gas law, kind of chemistry, so you can argue chemistry too, but the gas law is called Boyle's law. What it says is that if you have a container of air, so if a container of air, that air, so these little dots are supposed to be the air particles like that. Well, those air particles are moving really, really fast. I have a visual in a second for that. And they're going to create pressure, which means that they're going to push on the walls, all right? And this right here is a movable piston, so we can move or change the volume, so the space that the air takes up, okay? So basically, Boyle's law says if you have a volume, an initial volume and pressure, and you change that system, the system itself in relation to pressure and volume remains constant. But if one goes up, the other goes down kind of thing. So if you notice here, if I start with a large volume and then squish it like this, so I decrease the volume, well, that's going to increase your pressure. So this little dial right here is supposed to show you that here's your initial pressure, and then this is the final pressure like that. So the initial conditions must equal the final conditions, is all this is saying. P1 V1 equals P2 V2. You can do initial and final, 1 and 2. The notation doesn't matter. What it's modeling is how you change the volume and how pressure changes. So as you make your volume smaller, the pressure gets higher. When you make your volume bigger, the pressure gets lower. That's the biggest thing you can, get from this. So like I said, I do have a visual of this, so let's bring that up. There we go. And here we go. So what I'm going to do is put some particles in here, right? Let's do that. There we go. I'm going to give it a second to kind of equal out, but I hope you notice that the particles are moving. So this is gas, so you can think of this as air. And notice that there is a dial here that's measuring pressure and atmospheric pressure. So this is 2 atmospheres, so it's pretty heavy because we usually live in 1. We're not going to worry about temperature today. Temperature is the physical motion of these things. That's the measurement of that. What I do want to show you is Boyle's law. So if we start here and we expand this and make it bigger, notice the pressure drops. And if we make it smaller, the pressure increases. And in this case, you can see that the top actually comes off here. But let me just reset this back here. And now kind of talk about it in terms of our lungs. Strangely enough, our lungs work this way. Oops, too much? That's okay. So what happens with our lungs is our lungs expand. When they do, we lower the pressure inside our lungs, so air rushes in. And then when we breathe out, we increase the pressure and the air goes out. So when we breathe in, we're not sucking in air as it feels like. We're actually allowing a pressure difference, and the atmosphere is pushing the air into your lungs. And then the lungs push the air out into the atmosphere. So that's actually how it works. And that's what Boyle's law is. So we actually need pressure difference to actually do this. So we actually can't take in air if there's no pressure difference. So that's another interesting feature of that. So this is just Boyle's law in terms of how we breathe. Another visual of the same thing. And of course, I have a little video of that, so let me do that. There we go. It's very quick, like a couple seconds.
Involve changing the volume and pressure of the thoracic cavity. By using the principles of Boyle's law, one can see that the pressure in the thoracic cavity is inversely proportional to its volume. When the intercostal muscles contract, the ribs are elevated. At the same time, the diaphragm contracts. These events expand the thoracic cavity, decreasing its internal pressure. The lungs expand, filling the thoracic cavity. The resulting pressure in the lungs is lower than that outside the body. Air enters the lungs until equilibrium is reached. When the diaphragm and the intercostal muscles relax, the thoracic cavity recoils. The resulting increase in pressure causes the air within the lungs to be expelled.
Okay. So more or less it's very similar to what I just said. So let me come back actually to this. So this is how straws work very similarly. We always think of straws, I actually don't have one with me right now, but we think of straws as we're sucking in the air. What's happening is we're lowering the pressure inside the straw so that the atmosphere could push the liquid into your mouth. So if you had a case where, not that you would have a case, I'm trying to think of some things I have around here, but if you had, like, you know, here's something silly. You have my water bottle, right? And I took a straw and I sealed it on top of it so that there's no air around the straw. The straw will work because it needs the atmosphere to push on. So in other words, if you have a really tight cap on your straw, like on your cup, the atmosphere can't push down, therefore you won't get air, won't get anything out of your straw. Now most straws are open to the atmosphere, like for example, I'm a pretty big Starbucks fan. You'll notice that if you put the straw in that container, there's actually an opening so the atmosphere can get into it. So it doesn't have to be a big hole, but it has to be a hole. So if you use a cork, for example, you won't be able to do it. You might have noticed that a couple times if you've ever used really tight straws or something like that. You actually can't physically do it. So this is showing that when you breathe into a straw, you're opening up your cavity, you're lowering the pressure, and the high pressure is pushing it into your mouth for the most part. And that's Boyle's law. As you increase the volume, the pressure decreases. As you decrease the volume, the pressure increases. So that's Boyle's law in a nutshell. And of course, if you took a more traditional physics and math class, you would measure these things, but these are the practical applications. This is how it's actually used in everyday life. So let's take a look at the anatomy of speech. Once again, I'm not going to go into this. In fact, it's not even something I'm going to test you on. The biggest thing I want you to really notice, though, are a couple things. So obviously our lips and tongue are a huge factor in how we speak. But this one, the vocal folds. So right in the larynx and there in the trachea right here. Because the vocal folds will actually act like things that we've talked about with tension, like strings. So even though these are clearly not strings, they have properties like strings. So it explains why things sound the way they sound. So these are the vocal folds. If you look at them, what happens is this is in your trachea, and this is the folds themselves. And I'll show you a video too, a really gross video. Sorry, a video of these vocal folds. Now, let me see. I just want to see quickly where I'm going here. Okay. Okay. So there's some more terminology, and I'll introduce this some more too. But when you're talking, you have vocal cords that actually vibrate. So I'm going to go ahead and put my hand on my throat, and I hope you try this too, even though you might look silly. Hopefully you're watching this, on your own. But do this. It's really interesting. Take your hand and put it on your throat, and then what I'd like you to do is just talk. If you don't know what to say, just say the Pledge of Allegiance, something that we all know, right? What you'll notice is that when you're talking, your neck actually vibrates. So your vocal folds are vibrating. So I'm going to tell you that unvoiced is when they don't vibrate. So that happens when you whisper. So try this. I'm going to say the Pledge of Allegiance in a whisper. I pledge allegiance to the flag of the United States of America and to the republic for which it stands. Yeah, so I know I sound silly, but it's cool, right? Because my voice, because I'm talking to you, is definitely vibrating, but if I start to whisper, it doesn't vibrate. That vibration's gone. So this is voice, and this is unvoiced. So those are two things that we call, or two examples of voice and unvoiced. And then phonation is the process of actually making audible, So phonation is me actually, talking, where vocal folds are more about, the vibration. So I could say, ah, so I can sing a little bit. So those are another example of voice, because they actually vibrate as well. Phonation is more of the talking part. So, another thing is, if you have no filter, so if you don't use your vocal folds, for example, or if you don't really use your lips to create the sounds that you might hear, you get a windy sound. So breathing, I'm exaggerating my breathing here so that you can hear it, but I'm not, changing my lips, my tongue, my vocal folds, and nothing's happening. So with that said, what you get is that, again, that whole windy sound. Now, when you have anything physically that's windy, it means all frequencies are present. So it means noise, just like if you take your keys. Here's my keys. I have a bunch of non-related mathematically frequencies happening at once here, so that's noise. Windy is the same concept, it's just noise. So you need something to actually adjust or make that initial sound or change that sound. So I actually have a balloon right here. I don't happen to have a balloon, but if you use your imagination, I blow up a balloon. Have you ever done it before, where you take the opening and you squeeze it in and out? What happens is you're changing the filter. So it go, I don't know, maybe I can find a video later for it, but use your imagination. You blow up a balloon, and you, instead of just letting it go like you normally would, that would be a no filter initial sound, but you could take a balloon and actually make a sound out of it if you squeeze the end of the balloon. So that's acting as a filter. So, again, talking about whispering, when you whisper, you can't really, you actually can't sing when you whisper. So you could try, you could go ahead and do that. But if I sing Twinkle Little Star and then switch to whispering with my hand on my throat, twinkle, twinkle, little star, how I wonder what you are. Up above the world so high, I got diamond in the sky. So, I hope you noticed that I get more tone, obviously, when I'm voicing, but when I do sing as a whisper, it actually all sounds the same. It doesn't sound like I'm changing the note. I got diamond in the sky, twinkle, twinkle, little star. I mean, you can see a little, hear a little fluctuation, but you don't hear as much as you normally would when you sing. So it's a really interesting concept. So that's because you're not vibrating your vocal folds. So if we were to graph this in lab, a whisper speech would look like this. In other words, we'd have a ton of frequencies present at once. Versus like the telephone lab, if you remember, we just had like 2 points, right? We had 2 frequencies only. So of course that corresponds to a much nicer sounding tone than, whispering. So once again, we can relate these concepts to physics, right? So I have the wave equation down here, frequency and wavelength. So if we have more tension, we change the velocity of your wave, so what it sounds like, right? Just like you take a guitar string and you make them more tense, it's going to sound higher. So if I want my voice to sound higher, I can actually make them more tense, just like this. And then if I want to make a lower pitch, I can loosen my vocal folds and make it low pitch like that. So those tension, even though this is not a string, it acts like a string. So as you might imagine, the tension affects it. And then the length does. So, I mean, we all know this, since we're all different. We all have different voices and different styles of voice. In fact, a lot of times that's why music's really interesting, is because people have different voices. Well, that's based on length too. So generally, and again, I'm going to generalize here, so it's not always true, but people who are smaller have smaller voices because the length is shorter. Shorter means higher pitch. And, people who are bigger have lower voices. So, I always think of the movie Green Mile. It's I don't know the name of the guy, but he's the big guy in that movie. I forgot his name. But anyway, but he's a huge, right? He's a big guy and he has a really deep voice, So if you have a really big guy, or if you watch like Game of Thrones, like the mountain has a deep voice, whatever your character is in your mind. But that's, of course, dependent on the length, and that's, the anatomy and biology of a person. But these, again, all relate to the wave equation that we learned. Again, this is just showing that same kind of concept right here. So actually, before I move on, I thought I had a video here. Must have missed it. I did, so give me a quick second. So if you're squeamish, you may not want to watch this right now. But I want to show you how the vocal cords actually physically move in this video. So it's interesting because I'm going to show you in a second 4 people singing a song, professional singers, but they actually took a camera watch and they put it up in their nose and they put it all the way down into their vocal folds. So they're singing with the camera, and this is them singing. Yep, this is it. So I apologize if you're squeamish, so maybe stop the video or fast forward it. But I actually think it's, although very disgusting, very cool. So here they are. Here's the camera going into each of their noses. Actually, you know what I might do, because the resolution's really bad, I might just do it like this. There they go. My sound is up all the way. Yep, it is. Okay. There we go. There we go. So these are all their vocal folds. And here we go. They're going to sing a very beautiful song. Gross, right? So, you know, if you're noticing that they're tightening their vocal folds, right, closing them, and to make the beautiful sounds that they're making, they have vocal training to train their muscle, which is their voice, to sound the way they sound. It's pretty cool, huh? I think it's kind of cool, even though it's really gross. Anyway, I'll let you watch it another time. But I just like that you can see the physical setting of their voices here. So we'll leave that there. So there's, I knew I had a bunch of videos. Okay, so falsetto. Is a type of singing that people do. Grab this. Sorry, I thought I had everything ready. Here we go. I'll let the ad go. Okay.
A common question my student.
Okay. So falsetto is a style of singing. It's not your natural singing voice. I'm actually going to let him kind of talk a little bit about it. But it's another special case of voicing. What happens is when you sing falsetto, and I'll show you the audio example of this in a second, is it actually changes the shape of your vocal folds. So this is a side view of it. So in normal mode, when you're normally talking, your vocal folds, like the video we just saw, are perfectly straight. When you sing falsetto, it actually creates standing waves. It's so crazy. So he's actually going to give you a more of a demonstration of what it means to have falsetto versus this other thing called head voice, but he'll talk about it.
Ask when they're singing is that head voice or is that falsetto? Inside this video, I'll show you the difference between falsetto and head voice, so you'll know how to sing with both to choose the best for your songs.
A little voice. So here we go.
Hi, I'm Chuck Gilmore with Power to Sing. The definitions of falsetto and head voice often disagree. I define them based on the condition of the vocal cords. Are the vocal cords connected or disconnected? When your vocal cords are disconnected, you are in falsetto. Here's a slow motion video found on YouTube of the vocal cords disconnecting. This is a scope of voice artist Mal Webb from the UK. In this video, he's making some unusual sounds.
So see that they're vibrating? They're actually making standing waves. Isn't that crazy? And then, of course, he's defining it as not connecting versus... So you have to not connect to have the standing wave.
The vocal cords suddenly breaking apart. This is falsetto. While in falsetto, you can see the edges of the vocal cords are barely touching as they open and close.
To make a standing wave.
A lot of air passes through the cords. Because they're in falsetto, there's little to no resistance to the air pressure from the lungs. You can sing high very easily in falsetto. You can also bring the falsetto voice down quite low, like this. Some
Some singers can bring falsetto all the way down to where you would normally sing in chest voice. Falsetto will not blend into the chest voice. In order to get back into the chest voice, the vocal cords have to reconnect. This usually involves a break-type feeling back into a connection. For men singing in falsetto, there's a significant loss of the lower overtones of the chest voice. I compare it to my Minnie Mouse voice. Oh, hello. Hello, my name's Minnie Mouse. For women, there is a loss of the lower chest overtones in falsetto voice as well. This can result in a breathy, airy tone quality. Also, if I try to lean into my falsetto by increasing the volume and air, there is little to no resistance. In fact, it seems to blow the cords further apart. Finally, there is some opinion that years of singing primarily in falsetto is a leading cause of the vocal wobble as you get older, because the vocal cords have lost their ability to adduct firmly. How can you tell if you are in falsetto and not head voice?
This video is pretty interesting. We're not going to watch the whole thing. I'm just going to change this link right here. Anyway, and you can learn about head voice as well. So the biggest thing is that this makes a standing wave, which is pretty cool, and I like that video because it shows that. So just to give you some perspective on, speaking voices, most men speak around 100 hertz and women speak around 200 hertz. Of course, these are generalizations, but just to give you an idea, if middle C is right here, women are a little below, but men are usually a whole octave lower. Children, like my daughter, she's actually a little higher than middle C like that, so around 300 hertz like that. So the air itself can actually change how you speak. We kind of know this already through helium. Not that you should do this, but you know that if you take in helium, you have that, Munchkin voice, right? That's because helium is a light gas, and light is easier to move. So F equals ma. This is a very famous physics equation. But less mass means less force, so it's going to go faster. Of course, acceleration is not really about speed. Well, it's a change of speed, but anyway, just modeling that case. You can actually have the opposite. You can have really heavy mass air, and your voice lowers. So actually, let me show you that. I have that video ready to go of Adam Savage doing this.
I promise to show you something really cool as long as you promise not to try it at home, okay? Okay. Now, everyone wants to know why my voice sounds higher when I inhale helium.
My simple fact is that helium is 6 times less dense than air, which means sound waves travel through it much faster, which makes my voice sound much higher. Now, the same effect can be achieved in reverse if I inhale something like
sulfur hexafluoride, which is 6 times denser than air. I inhale some of that. And my voice gets really low, although somehow I'm still funny. It's scientific!
I love that, because it's so, you don't expect that to happen. It's just so funny, but yeah, he explained it. Heavier gas is a slower speed, a lighter gas is a higher speed. So the mass of the air itself can change what you actually sound like as well. We don't usually change the air, right? You usually just stay in air. It's not like helium or sulfur hexafluorides. We never notice these changes, but if we went to a different planet, for example, we might sound different, depending on how heavy the air is. If we went to Mars with little atmosphere, our voices would probably sound like this. And maybe we go to Venus where, the atmosphere is much more dense, we might sound like this instead. So very interesting perspective on, on how air changes what we sound like. So now in this part of the video, we're going to kind of look at another, like I said, something that changes our voice is the filter of our voice. And that is just our air cavity in general. So our air cavity kind of acts like a closed pipe. So the closed end of the pipe is our vocal folds. So yes, there's some air that passes through there, but generally they're They're more closed, so it forms a node at that point, which means our mouths provide the opening for our closed pipe system. So what you get is you get these resonances. So there's certain waves that get trapped in your pipe, in your air pipe, that sound louder because they match the frequency. This is way at the end of my slide, but this is why singers, especially opera singers, sound really loud when they hit certain frequencies, right? When they say la. So when they go to this special note, they might actually sound louder because they actually hit a resonance because of their closed pipe nature. So, just like before, if we know their fundamental frequency, we can get their resonances. So that's pretty good. And this is pretty standard, not standard, but generalized measurements of the windpipe of men and women. So if we were to graph this like we will in lab, this is what's happening. So so what happens is our air or vocal folds make lots of different frequencies happening at once. But then our vocal tract has resonance, means that we're going to have peaks at certain frequencies. Now, if I took this right here and cookie cuttered this, put this on top of that, we'll get this. So we have a combination of our vocal tract and our vocal folds. So when we model this on the computer, our models will look like this, showing higher resonances in certain places because of our pipe and different frequencies based on our vocal folds. So everybody has their own pattern, if you will, of the way they speak like that. But it turns out that regardless of our physical pipe right here and vocal folds, that we have what are called speech formants. Now, speech formants are actually related to vowels, and it turns out that regardless of who's speaking, we get patterns that are very similar in terms of resonant frequencies. It has to do with the way we're opening and closing our mouth and our tongue placement, so you can kind of see how ah is a very open sound. Ah. E or I. Notice right here, or heed. It's a very closed sound, or pool is a very closed sound to pool, like open in the mouth, pool, like that. E, ah. So the tongue placement, the opening in your mouth, the throat placement, ah, e, oo, all change the shape of the graph. In fact, our lab is going to be us saying these speech formants and seeing if we make these patterns. Or more or less, you're going to see that they may not be exactly the same, but we should see that there's going to be distinct resonances, in these pipes like this. So, regardless of who says it, we see a very strong peak around 200 and around 2000 for E. For ah, it's 500 and 1000, I'm rounding, and ooh is around 300 and 900. So these were discovered that regardless of who's saying it, we have these speech formants. So, this is plotting the two types of frequencies we hear, like heard and had and head and heed. Heed has a very high frequency for the second harmonic, but low for the first, and vice versa. This has like right in the middle. So these are just saying some studies from Scientific America of these speech formants. So again, if you think about our closed pipe harmonics and how this kind of works, like I said, ah is a very open mouth saying. So I know you might sound silly, but try it. Go ah. In order to do that, you have to open up your mouth. So you have a higher first frequency than second frequency when that happens. E, you have a higher tongue. E, so you're hopefully noticing where where your tongue and lip placements are for these. So these are the vowel production. So ah, e, I, o, oo. You're going to do this in lab and actually say all the vowels. Consonants, on the other hand, are very harsh sounds. They're more windy. They don't have really a good tone to them. So, for example, when you say a consonant versus vowels, if you say not T, but T, the sound that it makes, T, and K, 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 T, T, P, P. It's very different. And again, try this experiment with me. But if you say, make the sound of a T, it's in the front of the mouth. So go with me. T, 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 for T, right? Time and token and I don't know, I can't think of any T's. Trees and take. That's a very front of the mouth kind of feeling. K is a back of the mouth feeling. Kick. Kite. I feel the back of my tongue in the back of my mouth. Kid. Keep. Kite. Kit. And then if you did kit, you have a K and a T, that movement is back front, right? K for, a K is in the back, but the T is in the front. Kit. So I actually feel that in my mouth. And then B, baby, boy, break, bob, balloon. It's in the front of the mouth, but it's not as hard as the T sound. It's more of a lip sound. Baby, born, boy. I could feel it here more. So it's a very different thing. Of course, when it comes to speech, consonants are important because you need diction and articulation so you can hear the differences between sounds. But vowels are good for singing. So people who sing professionally will actually distort some words. So instead of saying, I'm trying to think of a word off the top of my head, like star or, I don't know, I can't think of a word right now, but they'll elongate the vowel tones because it's better for singing, like star, may not, star. They might cut off the R so that they leave the ah, star. As soon as you do the R for star, it kind of cuts the sound off, so they can, modulate their sounds to sound better. Mercy. So when you say something like mercy, mercy, C is a harsh sound, but the E at the end, mercy, can be held for a long time. Whereas, if you, the K kind of closes that sound. So, singing is actually very important to sing with vowels, versus singing with consonants. And then, of course, if you ever notice, like, really, again, professional singers, you can see that, I always watch Whitney Houston or Mariah Carey or, those are some of my favorite, artists. But anyway, if you look at their mouth, you could see that their mouth is usually open. They're setting the positioning of their jaw and their lips and everything to make that the best they can. They have years of training to do that. So it's not, some people, yes, they wake up and they're amazing singers, but, with just like learning a sport, you can learn to sing if you know how to position your voice and how to, make the proper muscle movements. And just like with a sport, you actually have to practice singing. I'm not a singer, but I practiced singing before, and it makes a huge difference. Because your vocal folds are muscles too, so you got to train your muscles. So you can't just go and sing, a song. A lot of professionals will warm up. You might even hear that because it takes time for the muscles to, just like running, you stretch before you run at least a little bit, not too much. Same thing. You don't want to overdo it because then it changes everything. So, like I said, singing with vowels, the beauty of it, so let me just make a quick distinction here, is when you sing with vowels, you actually highlight more of the vocal tract, right? Because that's what this is happening here, is when you say Father, this is the resonant frequencies that are happening here. The problem with singing with vowels is you lose articulation, right? So you don't get the clarity that you normally get if you sing with vowels, which makes sense, hopefully, because you don't say the words the right way. So the last thing is the singing projection or formant here. So this graph here is to show you that if you are like a professional, like an opera singer, it doesn't have to be opera, but if you look, this is ordinary speech, so this is relative intensity, so how loud, right? So this blue line peaks here, and then it swiftly goes down as you get higher pitch. You don't get very loud. Then you have the orchestra, which actually models very similar to speech. It's pretty interesting, right? So you peak at the lower end, less than 1,000 frequencies. So like right in the middle of the piano here, it's pretty loud. But after you get to the higher notes of the piano, they get softer. That's kind of what's happening here with an orchestra accompaniment. But all of a sudden, this red line is a singer, and all of a sudden, at very specific frequency, they're louder than the orchestra. That's crazy, right? Well, this is because of a sing-in formant. So just because they find the right frequency that matches the standing wave of a closed pipe in their throat. So you get a dramatic increase in their resonance, which is pretty amazing. So this is just all of that explaining, exactly what happened. So they basically just take their closed pipe and they found the right frequency. So I actually have two things. Oops. Oh, and I'm messing this up. First of all, I'm going to post this. This is really interesting. Why can an opera singer be heard over the orchestra? Basically, this whole article by Scientific America does explain what I just talked about. So you don't need to read it, but I'll post it because it's interesting if you are interested. But let's hear an opera singer. This is from Il Rigoletto, La Donna Mobile, The Woman Moves. But just give you a singing voice. You can hear how loud he is. Here, I'll do this because it's so like poor quality. So watch as he gets higher. There it is. So, anyway. So he's talking really soft here again. And then let's give him a second. So naturally he can control the volume of his voice. But if he hits a certain note, it's going to be higher than the other notes. Here it comes. Not yet. It's the yay. Not this one. This one. So loud, right? There it is. So even though he was singing, I mean, he's a trained professional, so yes, he can project his voice very well anyway. Oops, I closed the whole thing. He can project his voice anyway, which is important, but he doesn't have to try as hard if he hits a certain note. That's a whole, if you ever seen the cartoon where the opera singer, breaks the glass. That's very true. That's because you're matching the standing wave of a closed pipe because of your air pipe in that frequency. So yeah, that's pretty much it. I just ended right there. So just to kind of conclude everything that we talked about, I'm actually going to go back to the first slide to talk about what we talked about. So, like I said, I'm definitely no expert in singing, definitely no expert in anatomy. But I hope you notice that we can connect physics to all of this. With breathing, we can connect it to Boyle's law, so it's a gas law. With speech, whispering is an example of noise, which is all frequencies present. The anatomy of the voice, so we can treat the air column here that you have like a closed pipe, which allows for speech formants and singing projections, so that allows for you to actually hit a note and actually sound louder. And how the consonants and vowels actually shape what you say based on the change of your pipe, basically these filters like that. So I hope you enjoy this lesson on the voice. If you're doing physics of music, there's a lab that's associated with this. You're going to look at the speech formants of vowels, and then you're going to look at consonants, and for fun, you're going to find your singing voice. Have a good day.